Okay, so we're getting really good at making clean energy from the sun and the wind. But let's be real. What happens when the sun goes down? Or when it's just not a windy day? Today, we're going to dig into the single biggest piece of the green energy puzzle. How do we actually store all that power?
I mean, that's really the question, isn't it? It's the ultimate challenge. We need electricity 24/7, but the sources we're relying on more and more, well, they just don't work that way. They're intermittent. So how on earth do you bridge that gap?
And that mismatch, the gap between when we make the power and when we actually need it, that creates something we like to call the renewable energy riddle. Let's get into it.
Think about it. We get the most solar power right in the middle of the day, when the sun is high. But when do we all get home? Turn on the lights, the TV, and start cooking? In the evening. It's this fundamental timing problem, and solving it is absolutely critical if we want a reliable, green power grid.
So, what's the solution? Well, in one word, storage. And no, I'm not talking about the little AA batteries in your TV remote. We're talking about massive grid-scale systems. We're talking about truly giant batteries.
What these things do is pretty incredible. They can basically soak up huge amounts of extra energy, say on a super sunny afternoon, and just hold on to it for hours. Then, the second we all start needing that power, they release it back into the grid. They're the buffer, the safety net that makes a 100% renewable grid even possible.
And when you're talking about storing absolutely massive amounts of energy, there are two technologies that are the real heavyweights. And you can forget about complicated chemistry for a second, because these are built on brilliantly simple ideas, using plain old water and using air.
So let's start with the undisputed champ, the one that's been doing the heavy lifting for decades, the water battery. The technical name is pumped storage hydroelectricity, or just PSH for short. The way this works is it's elegant. It's really just gravity doing its thing. When you have extra, cheap electricity on the grid, you use it to power a pump that sends a whole bunch of water up a hill into a reservoir. That's it. You've charged the battery. Then, when you need that power back, you just open a valve, let the water rush back down through a turbine, and boom, you're generating electricity.
And get this. This is not some small experimental idea. Pumped hydro makes up about 95% of all grid-scale energy storage in the entire world. It is the proven dominant technology we rely on right now.
So yeah, PSH is super effective. You get about 70 to 80% of the energy you put into it back out. And these plants, they can last for a century, sometimes even longer. But there's one big catch, and it's geography. You need two things you can't just build anywhere. You need hills, and you need a lot of water.
Okay, so what if you don't have a convenient mountain handy? What's your next move? Well, that brings us to our second contender, the air battery, or as it's officially known, compressed air energy storage, CAES.
The idea here is just as simple, really. Instead of pumping water up, you use that extra electricity to power a massive compressor, and you use it to shove a huge amount of air into a big airtight space underground. Think an old salt cavern or an abandoned mine. You're basically storing energy in the form of super pressurized air. To get the power back, just let the air out through a turbine.
But here's where it gets tricky. If you've ever pumped up a bike tire really fast, you know the pump gets hot, right? Well, imagine that on an industrial scale. Compressing air creates a ton of heat, and that heat is energy. What you decide to do with all that heat is the single biggest thing that determines how good your air battery is.
So there have been two main ways to handle this. The first generation systems, called diabatic, basically just let all that heat go to waste. In fact, they were so inefficient, they actually had to burn natural gas just to heat the air back up before releasing it. But the new way, the much smarter way, is called adiabatic CEAS. It's a game changer. It captures that heat, stores it in a separate system, and then uses that same heat to warm the air back up on its way out. No waste, no extra fuel.
So there you have it, our two main contenders. One uses water and gravity, the other uses air and pressure. So how do they really stack up against each other? And what does it all mean for where we're heading?
This really lays it all out pretty clearly. PSH is the veteran, right? It's been around forever, it's got that huge global share, and it's very efficient. CAS is the up-and-comer. But look closely at that efficiency line. The new adiabatic version of CAS, it's right up there with PSH. So the biggest factor, once again, comes down to one thing: location, location, location. Do you have hills or do you have caves? And yeah, this really drives that point home. You can just see that huge jump in efficiency from the old-school diabatic CEAS to the newer systems. It proves that with some smart engineering, managing that heat, an air battery can be almost as good as a water battery.
But here's what's so cool, and maybe the most exciting part. That line between you need hills and you need caves, it's starting to get blurry. People are now figuring out how to use old abandoned mines for both systems. A deep mine shaft can give you the height you need for pumped hydro, and of course the caverns are perfect for compressed air. This one idea could open up literally thousands of new spots to build these giant batteries.
Which leaves us with a final massive question. We have these incredibly powerful, yet simple solutions based on basic physics, and they're getting smarter and more flexible every single year. So, are these giant, simple batteries the key we've been looking for all along? Are they the thing that finally lets us solve the renewable energy riddle and build a 100% clean grid? The potential is just enormous.